Hello, welcome to our last week of lecture series of the program. It's not the end of the program. And we start by the series by Vladimir Dotsenko from the University of Strasbourg, who will give us an introduction to Koszul duality.
Thank you very much. Thank you for inviting me here and suggesting to give this mini course. I'll try to, in full generality, Koszul duality eventually becomes a very abstract thing, but I will try to center everything that I will explain today and tomorrow around the one main example related to the topic of this semester, related to quivers and Donaldson-Thomas invariants. So somehow that example on which we will be trying to test various general approaches and ideas, which it concerns two recent papers in two recent projects in which I participated. So one with Evgeny Feigin and Markus Reinecke, and the other also with Piotr Kucharski. This also is related to another thing that I've been doing a few years ago with Sergei Mozgovoi, and maybe towards the end of this talk I will talk a little bit about the connections with that story, but probably realistically that part will mainly remain sort of outside the scope of this mini course, and that I'll be happy to discuss in the following days. I am here for the whole month, so I don't have any excuse to not talk about that privately. And that example is the following. So let me just define some algebras that we will be looking at during this mini course. So I take Q as symmetric quiver. So for example, you can take this one, two vertices, one arrow back, one arrow forth, and one loop at one of the vertices. So, but in any case, symmetric means that for two different vertices, the number of arrows from A to B is the same as the number of arrows from B to A. There are no other restrictions, so there can be multiple arrows, multiple loops, whatever you prefer. So then, the algebra, so AQ, it will be a supercommutative algebra. I have to say that probably there will be many moments when I will be saying commutative, meaning supercommutative, so all the elements will always have their degrees, and those degrees will be you should think of as homological degrees, so they will be creating all the signs in commutativity, anti-commutativity, and so on. And so it is, this algebra has generators A, I, K, where I is a vertex of the quiver and K is a non-negative integer. Then the degree of A, I, K will be equal to, well, I will change, so slightly change the convention that you can find in our paper. So it's 2k plus the number of loops at the vertex I. So, for example, in this case, so you will have the generator. So if you number these vertices 0 and 1, sorry, why am I doing that? Yeah, so you have this sequence of generators at the vertex 0, sequence of generators at the vertex 1, and so this vertex has no loops, so the degrees are going to be 0, 2, 4, and so on. And here you have one loop, so the degrees will be 1, 3, 5, and so on. And supercommutative means that to begin with, we are asking that these generators are commuting. Since they are of even degrees, these generators are anti-commuting, and the first group of generators commutes with the second group of generators. So relations will be this supercommutativity and slightly more interesting relations. And these slightly more interesting relations, well, you can write them formally, so let me first write them formally. The sum A, I, K1, A, J, K2, the binomial coefficient K2 choose P is equal to 0, K1 plus K2 equal to K, and you have to impose these relations for all I and J vertices of the quiver, and for all K, and for all P, where by Mij I mean the number of arrows from I to J. So so let me rewrite, so better way to write these relations, let's introduce a formal variable z. Yes.
I have a question about the degree. Does it play a role apart from its parity?
It will, so for supercommutativity, of course it doesn't. It will play a role when we will start writing some characters taking into account the degree. Because if you just keep track of the parity, this means that at each vertex you have an infinite space of generators, so you have no way to write any meaningful generating functions for dimensions of anything. And setting up degrees like that means that this algebra is multigraded with finite dimensional graded components, so you can write some generating functions and use them for some things and characters.
Okay, thank you.
Let's write this current formal generating series some aik z to the power k, and then somehow these relations are equivalent to saying that ai of z times the derivative of order p dp dzp is equal to 0 for all p between 0 and mij. So this all k greater than or equal to 0, these, if you extract individual coefficients of that, the coefficient of z to the power k is going to be proportional to the relation number k. So that's, and this is already much nicer, because you can also say, so in other words, ai of z, a j of w, if you take another formal variable w, then this vanishes on the diagonal z equal to w of order mij, so which is an even nicer way to think about it, perhaps. So now, so this is, well, maybe I should also say that that in this particular example, just to keep track of it, so we had, so I told you that these are degrees which ensure anti-commutativity. And then it turns out that the second group of relations in this case, you won't have any relations with any extra relations between A0 with themselves and A1 with themselves. The only relation will be A0 of Z, A1 of Z is equal to 0. So the second group of relations is just coefficients of this only power series in this case. The product of this with this is 0, the product of this with this plus the product of this with this is 0, and so on. So now, yeah, so this is the example that we're going to keep track of in the general context of Koszul duality. And so the particular feature of this example that makes it reasonable to study it using Koszul duality is that these algebras are algebras with quadratic relations. So observation, relations, one that is supercommutativity and two are quadratic, meaning combinations of products of pairs of generators. And it so happens that in general, there is this kind of general phenomenon that since a product is something which we define multiplying two things, of course we can multiply three things, but the product of three things, it's the iteration of products of two things. So the fundamental notion is product of two things. And that two is precisely responsible for the fact that algebras with quadratic relations have a much more remarkable theory than algebras with relations of arbitrary degrees. So this, if we live in the universe where the basic structure operation accepts three arguments, then algebras with cubic relations will become very important. But since in our world product takes two elements, algebras with quadratic relations are more important. Yeah.
I have a question, maybe it's too early, but I am not sure I will be able to ask later, so let me ask now. In some works you find this dt invariance in terms of this Koszul algebras and so on. But these are just for quiver with one vertex.
No, it's
those working for...
This works for arbitrary symmetric curve. Somehow it's absolutely general, but we will get to that. So for now, so I haven't yet even tried to say how these are related to any dt invariance. This is just for now, just some algebras. So in general, so there are several types of dualities for associative algebras which are closely connected for quadratic algebras, and otherwise they sort of diverge completely. So there is somehow the Koszul duality, which let me write three of them, and then I try to say what they do. So there is the bar duality, and there is the quadratic duality, which so this only exists for quadratic algebras, for algebras with quadratic relations. So Koszul duality, it kind of relates an augmented algebra A, and maybe I should already say that augmented means that we fix with augmentation from A to the ground field, algebra homomorphism. So we choose a way to algebras that I'm going to consider will be mostly associative algebra with a unit, and augmentation provides a way to split out the unit because once you have such a homomorphism, you can look at the kernel of the augmentation, so take the unit away. And since I wrote that, I should probably say that most of the things that I will be talking about will work over really an arbitrary field. In some of them you will need a field of characteristic 0, but beyond that, yeah, it won't really matter too much. So if you prefer to think about K as for complex numbers, that's perfectly fine with me, and occasionally I will write K to emphasize that it's sufficiently general, but it wouldn't really matter too much. Yes, so Koszul duality relates in augmented algebra A to so the algebra, the X algebra of the of K viewed as a module using the augmentation, but somehow, to be completely honest, if you want, if you just view this, so X, normally people write, so it's the derived home from K to K. But strictly speaking, if you just consider the derived home with its algebra structure, you forget a bit too much of the information, and it's better to consider the derived home with an A infinity algebra structure to consider some higher operations on it also. But so here you perhaps want to consider it as an A infinity algebra. So in any case, well, yeah. So this starts playing a role at some point, but for some purposes, just looking at X is already good enough, and this kind of duality comes from the is mainly important when you care about modules over your algebra, because somehow this viewpoint allows you to find some relationship between modules over A and modules over the X algebra, and that was somehow one of the first instances where Koszul duality appeared in work of Beilinson, Bernstein, Gelfand, relating, which I will mention a little bit later on. So the Kobar duality relates an augmented algebra A to its bar construction dA, which is a differential graded algebra, even if the algebra A itself did not have a differential, and somehow by so it's a very it's a very fun differential graded differential graded co-algebra, excuse me, it's in any case, so it's a very one bit of intuition that this sort of duality provides, which will be very important for us at some point, is that sometimes it's very beneficial to replace a complicated algebraic object by object which is free, but the price to replace it by a free object is to take a free object with a differential. So you hide all the complexity of what you are doing into the differential. So in this case, this is what the Bar-Kovar duality does. In the more classical case, so in commutative algebra, there is this Koszul-Tate resolution of commutative algebras, which on the physics side is closely related to the BV formalism. So somehow the idea of hiding complicated things into differential, happens everywhere, and it is a really important idea. But the point is that so these two dualities which are closely related to one another, so there is some kind of close relationship between the two, which I will return to later on. But both of them, they require some rather high level of algebraic complexity. So either you have to work with A-infinity algebras, or you have to work with very big differential graded co-algebras. So it's something which is easy to define, but any kind of hands-on computation becomes a little bit painful in reality. And that is where the last bit, the quadratic duality, comes into play. Because quadratic duality, it's only available for algebras with quadratic relations, but it's very easy to define. All the computations are very manageable. So for practical purposes, it's really wonderful, and that's why there is something very special about quadratic algebras, that there is a much more direct, much more hands-on way. So in some sense, this gives the hands-on way to manage the more conceptual previous dualities. And so let me say, use the rest of this board to tell you what the quadratic duality does specifically, and then we will start. Already there we can examine our examples and start somehow start understanding something. So if so let's take let's write these usual things. Here T of V, so V is a vector space. T of V is the tensor algebra of V. So the direct sum of tensor powers of V. R is a subspace of V tensor 2, meaning that you really have a combination of products of pairs of generators, and these brackets mean that I consider the ideal generated by R, which means that you take the for each n, so for each n you take the sum of all the consequences of R. You multiply it on the left and on the right by something, so that so you take and you take the sum over all n. So this is this ideal generated by R. Then so the quadratic dual where you put this exclamation mark over A is defined as follows. You take the tensor algebra on the linear dual of the vector space V, and you have to impose the quadratic relations, and the quadratic relations you define in the following way. So you have if you take quadratic elements, so this is you take the quadratic elements in the tensor algebra of V, quadratic elements in the tensor algebra of the dual, you have a natural pairing where you pair the first with the first, the second with the second. And then our dual is the annihilator of R. So R lives inside V tensor V, and R dual is what annihilates R for this natural pairing. One thing that I want to mention to you is that in our case, where things are supercommutative, elements have homological degrees, for this pairing, these degrees, well, the parities of degrees will be important, because when we compute this pairing, so if you have here psi tensor eta tensor V tensor W, then this pairing, so to pair psi with V, you need to first move V via eta, past eta. So it will be -1 to the power degree of eta degree of V multiplied by the evaluation of psi on V, eta on W. So somehow I just want to draw your attention that the sine rule, it's everywhere, so it's always interferes with various things related to when we use the symmetry isomorphisms of tensor products. And that is extremely important to remember, because otherwise formulas will be wrong, nothing will work. Because eventually we will use all these things to construct some chain complexes, and if you don't take care of things like that, the differential in your complex will not square to zero. So it really is crucial to remember this at every single moment. But with this little exception, everything is perfectly fine. So you started with one algebra with quadratic relations, and now you have another algebra with quadratic relations. Okay, so I will erase some parts of this, and well, actually, yeah, no, this is fine. Right, so some observations. I suppose that one very important observation is that if A is supercommutative, then the quadratic dual algebra is necessarily of the form U of G, where G is a Lie superalgebra. And that we can relatively easily see from the definition for the following reason. So, well, let's for simplicity assume that A were just commutative. So that all the generator among the generators. So what does it mean? So this means that if A is commutative, our space of generators contains all elements like that, where xi a basis of V. So the generators must commute with each other. So our relations contain all the commutators. And then somehow you start thinking, what is the annihilator? So the annihilator of R, in particular, must annihilate every individual commutator. So if you have, so in V star we have basis xi dual xj dual, since our pairing just pairs the first factor with the first and the second with the second, well, maybe let me write xp, xq. Then somehow you immediately see that that the annihilator of all the commutators is the linear span of all anti-commutators. So of the linear span of xi xj minus xj xi is the linear span of xpxq plus xq star xp star for all p and q. And then if our algebra is not has some extra quadratic relations, this means that you won't have all anti-commutators but some linear combinations of anti-commutators. But at least you will always have, so a dual will be the, you can write it as T of V star modulo all anti-commutators modulo some linear combinations of anti-commutators. And so this immediately shows you that your linear combinations of anti-commutators will be precisely the relations in some. So linear combination of anti-commutators you can view as relations in some superalgebra. Superalgebra in this case generated by odd elements. So somehow, so this is the universal enveloping of the algebra generated by V star and some quadratic relation, some relations. It will be beneficial, well, yeah, I still have a few minutes. It will be beneficial to look at some example. So let's take this example. So let me maybe now denote this. So to save some space, I will call elements here AK, elements here BK. So we remember that these are even and these are odd, and the relations are A0, B0, A0, B1, plus A1, B0, A0, B2 plus A1, B1 plus A2, B0. So these are the relations. And we also, so maybe let me also write AI, AJ minus AJ, AI. So these are the commutativity of A, AI, BJ minus BJ, AI, A commutes with B, and BI, BJ plus BJ, BI. This is the fact that BI's are odd. So now we go to the dual. So on the dual level, we will have generators AI star and BI star, so now the generators AI star will be, they will we will have to, so because we had commutators and anti-commutators here, this means that the generators, that the relations on the dual level will be linear combinations of these commutators and anti-commutators. And it will work in the following way. So the relations will be as follows. So AI dual, AJ dual will be just because there are no other things that involve two letters A, so we will just have anti-commutators and all anti-commutators, and that's it. Similarly, for the letters B, we will have their commutators, and that's it, because there are no other relations involving B. For relations involving A and B, it will be a little bit more interesting, because if we only have these, then we see that all the relations are linear combinations of anti-commutators. But somehow we also have these relations, saying that, for example, A0, B0 is vanishes. So in fact, so for A0, B0, we'll have both, since they commute, we'll have both A0, B0 and B0, A0. So on the dual level, there will be nothing. There will be no relation between A0 and B0. If we look at A0, B1 and A1, B0, so I claim that in fact the relation will be that the anti-commutator of A0 B1 minus A1 B0 will be equal to 0. So if we didn't have this relation, those would be just 0 independently. But since we also need to annihilate this sum, we need to compute their difference. They individually will not pair 0 with this sum. Then A0 B2 will be equal to A1 B1 will be equal to B0, and so on. So somehow this recipe of computing pairings. So, well, first of all, I have to say that, of course, in this computation, we are there is some kind of, well, I wouldn't say that we're lucky, there is some built-in luck, so to say. In principle, we have that space of generators are infinite, but there is this extra homogeneity. So in this relation, in each relation, we combine products with the same sum of indices. So here, 0 plus 1 is 0, so 0 plus 1 is 1, so here this total degree 2, and so on. So because of that, we don't have to deal with any infinite series. All the computations are formal computations with some finite dimensional vector spaces, and this computation give us this thing. So we have the anti-commuting generators AI star commuting generators bj star, and we have these linear combinations of anti-commutators. So the anti-commutator of ai and bj, if you want, only depends on a plus j. So you can think about this relation in this way. Okay, so maybe, I don't know, it is a reasonable moment to stop, right?
Yes.
Okay, great.
Questions?
Yeah?
How hard is it to prove every quadratic algebra is Koszul?
Oh, not every quadratic algebra is Koszul.
Very hard.
So it's not possible. Yeah. Yes, it's a great question. So in the second lecture, I will start with elaborating on that. So basically, what happens is that this quadratic duality exists for whatever quadratic algebra, but you have to impose extra condition of an algebra being Koszul for that duality to be useful for something. That's the point.
Other questions?
Yeah.
So this grading on vector space somehow help us to define that map. Is it correct?
Well, it's...
If I have infinite dimensional vector space, then I can't have that map.
No, if you... the pairing always exists because the tensor product is well, yeah, so you know your space is infinite dimensional, but you still have the you still the tensor product will be a finite linear combination of decomposable tensors. No, I mean there is absolutely no problem with defining this for an infinite dimensional vector space. It's just that after this map is defined, you still need to compute the annihilator, and that becomes more complicated for a general infinite dimensional vector space because you need to solve a system of infinite number of equations with infinite number of unknowns. So to define the pairing, you don't need anything but to actually to talk about the annihilator, to understand that annihilator is actually defined as an algebraic object. You don't need to take any completions and so on. That
Okay, so let's thank Vladimir again. We'll stop the recording for now.